So we can examine whether we understand the concept of clockwise, anti-clockwise moments and what causes clockwise and anti-clockwise moments by looking at an experiment. This is typically an experiment that we should be performing actually in order to examine on the conditions, but given the situation, we are only able to do it as a thought experiment. So there is a meter scale which is suspended at the 50 centimeter mark from a rigid support, and at that point of time it is perfectly balanced, which means sigma f is equal to 0. The task that is given to you is there is a stone or something like that, an unknown, an object with an unknown mass. Typically what I would do is in the laboratory, I just ask you to go outside the laboratory and pick up a stone and bring it back. A sizable stone, not much bigger than your own hand, like a bunched fist. And I'll then give you a 50-gram mass or something like that, a 100-gram mass, depending upon the size of the stone you bought. And by using this setup, ask you to find out the mass of the unknown object. So you know this one's mass, you don't know this one's mass. Can you use this to find out the mass? So I give a specific situation. Typically, I would allow you to explore after that, but since it is not possible, I give you a specific situation in which the 50-gram mass and the unknown object, in this case, have been placed 5 centimeters from the end in both cases. All right. So it will be at the 5 centimeter mark here and the 95 centimeter mark here. And then I tell you that as you set this up, there is a equilibrium that is obtained. It's a static equilibrium. That means it's neither rotating this way nor that way, and it is steady. So then I asked people, what now can you tell is the mass of the stone? And almost everybody in the class, if not everybody in the class, recognized that the mass is of 50 grams. So then when I asked, what is the reason? Why do you say that the mass is 50 grams? Then a student said correctly that the real reason I feel is because the place where the mass is suspended is 45 centimeters from the center and 45 centimeters from the center on the other side also. In other words, the length from the axis of rotation to the line of action of force. Remember that the line of action of force in both cases is like this. They are both pulling towards the center of the earth, parallel to one another. So that being the factor, I was asking some other student that why is that length the factor? How do you know that the length makes a difference? So then Rudra said that I know it because if I move the stone a little bit away from the point where it is right now towards the end, moving it towards the end, as I heard him say, then he said that that will cause a rotational motion to occur in the scale. And then I asked in what direction, so he said it's going to go in the clockwise direction. Then I asked a few other students if they agreed or disagreed with what Rudra said. Some of them agreed, Golyan disagreed. So Golyan says that no, I don't think it's going to go in the anti-clockwise direction, that it is going to go in the clockwise direction. So now we are trying to understand how do we decide whether it's going to go in the clockwise or anti-clockwise direction. Okay, so that's the point we are at the moment. So yes, now further thoughts. People are saying in the chat that the key that we are looking to is torque. So they are saying we have to look at the torque. So I ask you, what torque? In fact, it will be better in this case if we use the other term for torque, moment of force. Okay, so how do we look at it? How do we examine this a little bit closer?
So
yeah.
So the force applied by both the objects are same, right? It's 50 grams by both.
Correct, exactly. So the
and
50 GF force.
Yeah, 50 GF. Yeah.
50 gram force. Okay, so for those who are not, we worked with gram force and kilogram force in class 9, right? So I don't have to explain that again. Yeah, okay. So at least one person confirmed, no need to explain. Okay. We say that the reason why these masses apply a force is because of the gravitational attraction. Gravity pulls both those masses. So therefore, there is going to be a pull from this in this direction, from this in this direction, and that pull, we can convert it into newtons, of course, but one simple way to do it would just be to call it a 50-gram force. Okay, so that is a force applied by a 50-gram mass. It's easier to keep it that way. Then carry on.
Yeah, so the force will be 50-gram force from both the objects, and then the only difference will be the distance, like distance from the midpoint, that's 50 centimeters.
Yes, absolutely. So that is why you can see that there is going to be a difference, because while the masses are the same, therefore the forces that they apply because of gravity is also going to be the same. The only difference that happens in Rudra's case when he says you move it outside is the length. And that length you will recognize is part of the torque, because torque is force times the perpendicular distance, the perpendicular length, etc., to axis of rotation. Okay, line of action of force to axis of rotation. So now let us apply the torque discussion that we have had to this situation, where we can say that there are actually two torques over here that are being applied. Okay, one is because of the stone, the other is because of the known mass. Okay, so I can say that the clockwise moment of force, that is the moment applied by this object, is equal to the anti-clockwise moment of force. So I can say anti-clockwise moment is equal to clockwise moment. Okay, and when this happens, then I will have sigma f is equal to 0. Do you appreciate this statement? Is it clear? Any doubt about it? Diva?
Yeah.
Diva, are you following these arguments so far? Any doubts or questions you may have?
Uh, Not as yet. I'll ask you. I'm still going over it.
Okay, so if you get stuck at any point, please check with me. Uh,
Yeah.
yes, that's right, Ishrat. So can you just make the statement then? Oh, okay, wait a little bit. I'll make one more statement and then you can make your statement. Which is that the anti-clockwise moment, that is the one that is causing this movement, is the 50-gram force, okay, times 45 centimeters, okay, which will be equal to the clockwise moment will be again force is again 50-gram force times original situation before Rudra fiddled. Okay, so 45 centimeters, and you can see that the effect in this case and that case, the LHS is equal to RHS, and that is why the two objects balanced. But since Rudra got into the act, and what he did was he increased the 45 centimeter. Let's say that he pushed it by 5 centimeters and he made it into 50 centimeters. So that changed into 50 centimeters. Okay. So then now obviously this equation does not hold true anymore. Okay. So then it's not equal to, and therefore there is not going to be a static equilibrium. But then this still does not tell us in which direction the object, the balance is going to rotate, or can it? is there information over there to say in which direction the object is therefore going to rotate? And now uh, you can tell what you wanted to say. Ishrat.
Yeah. Yeah. So I was just asking if, like, the bigger the distance from the axis, the object. So the bigger the distance, the more the torque, right?
Exactly. So isn't that what comes out in this equation?
Yeah.
Right. So over here it will be 50 times 45, whatever that happens to be. Can somebody do the math and tell me? I can teach or I can do math. Apparently I can't do both. And now I've dropped my blue marker and I can't find it. Okay, doesn't matter. Come on, tell me quickly.
2250 GFC. 2250.
22. That's on
50.
the LHS.
Yep.
2250 gram per centimeter. Okay, this is something weird, but for the time being, let us ignore that. And on this side, of course, it's 2500 gram per centimeter. So forget about the units, bunk the units. Okay, just look at the numbers. As long as both units are the same. Okay, you can't simply bunk the units, but both units are the same. So we are not comparing apples and oranges. We are comparing apples and apples. And then you can see that instead of writing inequality, I can now actually say which side is going to be greater. I mean, you could do that even in the previous step, but now that we have done the actual calculation. So the clockwise moment side is therefore greater than the anti-clockwise. And that is the reason why Kolyan's observation is accurate. And that is the reason why Rudra will now correct his observation. Is that fine?
Yeah.
Rudra, okay?
Yeah, sir.
Right?
So could you also think of the distance as positive and negative, as in?
No. So we are not looking at displacement, right? So we are not saying that this is the center and one object was displaced in this direction, another displaced in this direction. So it is the distance from the axis of rotation to the line of action of force.
Yeah, but what I'm saying is, so then if it's negative and positive, then it'll help us know the distance. Sorry, the direction.
Torque. I mean, yeah, the rotation. Yeah, I suppose you could say that you could keep this as a positive rotation and keep this as a negative rotation. But since we already have a way to define that anti-clockwise and clockwise, and that is what is expected in your syllabus for you to know. So plus or minus, if you can go with that, but in the interest of the syllabus, I would like to keep it as clockwise torque and anti-clockwise torque, or rather clockwise moment and anti-clockwise moment. Okay. So,
yeah.
Any other question about this point? All right then. So I hope that makes this point clear. And of course, when you get back to school, we will do some experiments based on this. In fact, there is an experiment that you have to perform. This particular experiment you have to perform as part of your ICSE practical examination in 10th standard. So you will learn to do this quite accurately and therefore get a better sense of what this idea of moments is all about. So I'm asking the question, I take the same meter rule, but this time it has been suspended asymmetrically. So this point over here, it could be anything. The only factor is this, it's not midpoint.
Yeah,
So,
it's possible.
so basically, it's not suspended through its center of mass. Okay. And then I dangle some known weight on this side. And I ask you, can this be done or not?
It should be, right?
It should be or it can be.
It can.
It can be. If it's hung with less than half the length. If it's hung with less than half the length. Yeah.
Butterfly. Okay. Okay, yeah, it can be, right? Because provided you have sufficiently large mass, and that is why I put 4 slots over here, then you can change these weights around a little bit and make it in such a way that the scale is balanced by this mass. So now, going again to the torque concept, you can say that yes, it is suspended at this point, rotation is possible, so therefore this is anti-clockwise. So anti-clockwise moment has to be equal to clockwise moment, okay, or in other words sigma f is equal to 0. But then let us say that this mass is known, m1, okay, so, and this distance is known, okay, let's keep this as L1. So what is causing the anti-clockwise moment is absolutely clear. It is m1 times L1. But what is not clear is what is causing the clockwise moment.
Center of gravity, sir.
But gravity pulling on what? Gravity is
The
there.
mass of the scale itself, I think.
The mass
Yeah.
of the scale itself.
Yeah.
Okay, so
Not,
I
I
put
don't think it should be the entire length. It should be the subtraction, right?
Yeah. The midpoint of the
Where
scale
were you,
minus the
Aristotle?
pivot point.
Is the whole scale like, is the 50 centimeter mark?
Yeah, like from the
Yeah,
center
50
of them.
centimeter mark, but then it'll be from the pivot point. The distance will be from the pivot.
Okay. So I mean, we are kind of quickly running out of time, but think of this problem. Okay, so the question is that what is causing the clockwise moment? Okay, so some people are saying it's the mass of the scale, and I wrote it down there, the mass of the scale, ms being mass of the scale. But then we trip up at that point itself. You say that, but the mass of the scale is the mass of the entire scale. Shouldn't we only take this proportion? Sorry, this proportion. Okay, because this proportion is on the other side. How will the entire mass of the scale count for the one that causes the clockwise moment? Okay, so there is a question there. Some people say no, it has to be the whole mass. Some people say no, it has to be the proportional mass. Tell us at what point it is hanging, then we will tell you, blah, blah, blah. But then there is another one. Length of what?
No, length and pivot, right?
Length
Yeah,
from
length from the midpoint to the pivot.
pivot to
The
Midpoint.
midpoint of
The scale.
The scale.
entire scale or only the one to the right?
Yeah, entire scale. Entire scale. Because of the weight acts on the weight acts on the center of the center of mass, right?
So that 50 centimeter mark there.
Yeah.
Okay. So you are saying therefore that the weight of the scale, that is the mass of the scale times the gravitational constant, acts at the midpoint over there. So therefore it will be the mass of the scale. Are you sure about the mass of the entire scale, or is it just the part on this side?
Entire scale. Entire scale.
Okay. Why do you say that is another question. And then the length from this point, that is from the axis of rotation up to there. So we can call that length as the LS. And then that is the reason why there is clockwise and anti-clockwise torques or moments become equal. Okay, so actually by doing this experiment, you can find out the mass of the scale. Do you get it? Because this will be known. You can measure this length. So this is known, this is known, this is also known, this is the unknown. So without measuring the mass of the scale, you can find out the mass of the scale. Is that clear? Incidentally, just want to point out that I left out G on both sides. Okay, and that's for obvious reasons, because G is there on the left side and the right side. So basically they cancel out. So we can just write it as M1 L1 equals MS times LS. So this is another interesting consequence of the same concept.